Let's walk through using Python to do some of the predictive AI analysis we were just talking about. I've got a file set up in what's called Google Colaboratory or Google Colab. It's kind of like Google Docs or Google Sheets. You can click on this link to follow along if you're interested. So we're going to use the same Wisconsin cancer cells data set as before. Um, I used Google Gemini, which is predictive AI, to generate a lot of the code in this file. And one thing I deliberately avoided was something that should be standard practice in predictive AI, but I didn't want to overly complicate this initial introduction. So I wanted to keep things simple, and I wanted to give you, the students, a challenge, identify what I didn't do here, but probably should have. And then later in the semester, we can go back and do it the right way. Um, so we already saw some microscope images. So in a Google Colab file, you can have a cell that contains text. So that's what I have here. If I double click it, you can see I've got like a header identified by using a hashtag, and then I just type some text. I can say, here comes some bold text by doing double star and then double star at the end of the bold text. And then I hit escape to be done editing that cell. And you can embed an image. Don't worry about how to do that. But you can also have a code cell that has Python code in it. You can do R as well if you like R, but I'll just be using Python. So this is saying like there's this library called NumPy. We want to use that, but we want to use a short name for it. So just NP is the standard thing. Pandas is sadly not related to the fluffy animal that's black and white. It comes from panel data sets. It's a way of holding data in something like a spreadsheet inside Python. Um, so this is saying where to get the data. This is saying actually read in the data. And then this is saying what are the names of the columns? So we've already seen this in the Excel sheet, but like the diagnosis, was it malignant or benign? What was the radius? What was the texture, etc. So right now, this file, I ran it already. I had it execute the Python code, but it's not actually running anywhere because it's not connected to a machine that would run it. You can see up here, there's this thing that says connect. And once I click that, then somewhere in the cloud, which means in a data center somewhere, some computer will start a process that can execute Python code. So I might as well do that now. So I click connect, and it takes a little while to connect. Once it does, it shows me how much disk space I'm using and how much RAM memory I'm using. We're doing very small problems here. That's not an issue of overflowing our RAM or whatever. But if you see that, that means it is connected to a computer in the cloud somewhere. Google is kindly allowing us to use this resource for free. And if you leave it sitting and don't touch it for like an hour, it will time out and shut down that computer in the cloud. And if you know you're going to walk away from it, you might as well be nice. And you can go to runtime here and say disconnect and delete runtime. So you freed up that computational resource for someone else. Um, so now I could come to each code cell and click the little play button. There's nothing in that cell, so it finished immediately. Click play here. It takes a little, a second or two to import all that stuff, but 4 seconds, I guess. And then I can click play here. And then I can click play here. So you can do each one of those. Or when you're in a cell, you can hit Control Enter and it will execute the cell. Or if you press Shift Enter, it will execute the cell and move on to the next one. So you could get through the notebook by just saying Shift Enter, Shift Enter, Shift Enter. Um, it turns out one of these columns has a space in its name and like right here, and that can make things hard later. So here we're saying replace all spaces with underscores. Here's some more data on the data set. We already, more information on the data set. Here we're saying like, what is the outcome of all these columns? Which one is the outcome variable? Uh, for some instances, it's nice, instead of having words like yes or no, malignant or benign, to have numbers like 0 is benign and 1 is malignant. So that's what we're setting up here. So if x equals m, then give me a 1. Otherwise, give me a 0 for benign. Um, so then here's the top 5 rows of the data set, the first 5 rows. Um, just looking at this, the first 5 rows are all malignant. So, and you can see the diagnosis binary version is 1. Here I'm also outputting the benign rows just to show that there are some in the data set. Um, so what if we want to use just a single predictor? Um, I've got 2 listed here, and what will happen is it will execute this line of code, and then this variable called try single predictor will contain this value. And then it will execute this line of code, and the same variable will get overwritten with this thing. So it will basically forget that first one. So if you wanted to run this later and use this one instead of that one, you could just switch the order of those lines. Another thing you could do, a hashtag means basically here comes a comment that's for humans to read and the computer shouldn't care about. So you could comment out this line like that, and then this line would run, and then this line would not run because the computer sees it as a comment. Um, so that can be a useful thing sometimes. Then in the next code cell, we're saying just go ahead and fit this model, how outcome is kind of approximately determined by whichever predictor we use, so compactness mean probably. And then we say, go ahead and fit the model. Fit is another word for training, and we're saying the model is learning to do a good job. So this is called machine learning. Um, and it says things went successfully. The loss function is 0.44. It took 7 iterations to get there. Remember, we saw in TensorFlow Playground that graph that was filling in and dropping off. It did a lot more than 7 iterations. But here we only needed 7. So that's fitting a single predictor model. Then we can try fitting a 2 predictor model, which is what we did in that Excel sheet where we had area and compactness and we drew a line, etc. And then we go ahead and fit that, and it says terminated successfully, got a lower loss value, and took a few more iterations. Let's try making some plots. You don't really have to worry about this plotting code. But we see a plot a lot like the one we saw in Excel, with some cells being malignant, some benign based on area and compactness. Another way to plot it is to take that score that we're doing, like weight 1 times predictor 1 plus weight 2 times predictor 2 plus the bias, and that just gives us a single number for each point, a score or a logit. And so we can use that as the x-axis. And then plot for each data point a 0 if it was benign or a 1 if it was malignant. But if we did that exactly, then all these dots would be on the y=0 line, and they'd just stack on each other and you couldn't really see what was going on. So here we're jittering them by adding a little bit of randomness just to make them not overlap. And then we're also drawing in the logistic function for this data set. So we can see it seems to be doing a pretty good job where the curve is near the dots over here and near the dots over here and smoothly transitioning from one to the other in the middle. We can also have it go compute some stuff like false positives and false negatives. So we're saying, like, here's the model we fitted, here's the data that we used to fit it, here's the column we care about for the outcome, and here's the threshold to use, like 0.1 or 0.5. When we say 0.5 here, that's just saying that that's the default, but we can still change it. So we're calculating, first we're calculating like how many true positives, how many true negatives, how many false positives, how many false negatives. And then we're dividing them in various ratios to get accuracy and precision or positive predicted value, or recall, which is also called sensitivity, or specificity, or F1, which again is complicated and we won't worry about it. And then we're giving back all those things we calculated. And then here we're saying, let's try a bunch of different thresholds. So 0.1, 0.3, 0.5, 0.7, 0.9. For each of those, for each threshold in the threshold list, go and compute all those measures like positive predicted value, specificity, sensitivity, record the name of the predictor we were trying, and record it all in a data frame. And then it says display the data frame. And we can see the thresholds we tried, how many true positives, how many true negatives, how many false positives, how many false negatives, accuracy, sensitivity, specificity. Remember, we want sensitivity and specificity to both be large. And then we're doing it again here for the two predictor model. So remember, this was just one predictor, and it says this predictor name over here. Then we do it again for the two predictor model, try a bunch of thresholds, and it has recorded the names of the two predictors. And then because it's easier in Python, why not just use all the predictors we have, or at least the 10, not the 30. So here we're constructing a formula that has all the predictors and trying a bunch of thresholds on that. And you can see here's the formula. It's saying try to predict diagnosis based on radius and texture and perimeter and area and smoothness and compactness and concavity points and symmetry and fractal dimension. It got an even lower loss number. It took more iterations. And we can see true positives and sensitivity and specificity. It's nice to see all three of those tables together. So here we're just displaying them all so they can all fit on one screen so you can see them. It would also be interesting to graph them all together. I will leave that as an optional exercise for you. So that concludes the videos for this module.